In section 4.2, we're going to look at least squares regression. Sometimes this is called linear regression. So the idea in this section is that we have determined there is a linear relationship between two variables. So if there is a linear relationship between the two variables, then we want to determine what that linear relationship is. In other words, for example, on our bear problem, if there's a linear relationship between the length of the bear and the weight of the bear, could we find the equation of the line that best describes that relationship? And we're going to revisit this problem in just a little bit, and we're going to do just that. We're going to try to find the equation of the line that best describes the relationship between the length and the weight of the bear. So if there's no relationship, if we determine there's not a relationship, then we're done, right? But if we determine that there is a linear relationship, the next step is to figure out what that linear relationship is. So, example, recall the golf data from section 4.1 shown below along with the scatter diagram. So I've just repeated the data, the golf data, which was the speed of the club head and the distance the golf ball travels. So I've got the original data here, as well as the scatter plot that we created on that data. We determined that a linear relation exists between the club head speed and the driving distance. We did that in section 4.1. So now let's find a line that describes this relation. So again, if we have a linear relationship, we want to find a line that describes what that relationship actually is. So how do we go about doing that? Well, one way that we could go about finding that line is we could just kind of eyeball it. So I could just kind of look at this data and I could kind of see like roughly how the linear trend is, and I could just kind of draw a line through it. So I could perhaps use this line in order to model the relationship between the club head speed and the distance. The trouble is, if I draw that line and you draw that line, we may not draw the same line. So we would like to come up with a way of being able to determine the best line. So suppose that this is my line. I want to come up with a way of getting the best line. Another way that I could find the line, incidentally, is I could just choose 2 points. Like I might pick this point right here and this point right here, and I draw the line between those 2 points. And if I do that, then I could use that as my model. So I'm going to do that. So I did that in a different color just so we could tell the difference between the two. So my red line here, I could use as a model as well. But which one would be better, the red line or the blue line? Or is there still another line that would be even better? Well, if I do what I'm saying here with the red line, this point right here is the point 99,258. So that point right there is the point 99,258. And that point right there is the point 105,277. So that point is 105,277. So I could, if I use that technique, I could use algebra to figure out what the line is that goes through those 2 points. Well, if I want to find the equation of a line that goes through 2 points, I can start by finding the slope, and then I can find the y-intercept. And then from algebra, if you will remember, the equation of a line has the form y equals mx plus b, where m is the slope and b is the y-intercept. Also, we can find the slope of a line using the formula y sub 2 minus y sub 1 over x sub 2 minus x sub 1, where x sub 1, y sub 1 is the first point, and x sub 2, y sub 2 is the second point. Now, again, this isn't going to usually be the best line, but it is one way that we could find a line that describes the relationship between the two variables. So I'm going to go relatively quick here. The slope of the red line here would be 277, that's y2, minus 258, that's y1, over 105, that's x2, minus 99, which is x1. Now, if I take 277 minus 258, that is 19. And 105 minus 99 is 6. So I have a slope of 19 over 6. Now, 19 divided by 6, that would be approximately 3.1667. In statistics, usually we will write our slope in decimal form rather than fraction form like we do in college algebra. Now that I know the slope, I know that my equation of this red line is going to be y equals 3.1667 times x plus whatever the y-intercept is. So I can find the y-intercept by using either one of the points that we found. So for example, I could use 99, 258. I can plug them in for x and y to figure out the y-intercept. Or if you prefer, you can use the 105, 277. It does have to be one of those 2 points. So if I use the 99, 258, that means that 258, that's the y value, equals 3.1667 times 99, the x value, plus whatever the y-intercept is. Well, 3.1667 times 99 is 313.5033. So I have 258 equals 313.5033 plus b. So if I subtract the 313.5033 from both sides, 258 minus that is negative 55.5033. So our y-intercept b equals negative 55.5033. So ultimately, my red equation is y equals 3.1667 times x minus 55.5033. This would be the equation of the red line. But is that the best line? Using that red line, and if I had this equation here, if I asked you to predict what a bear would weigh if it was 103 centimeters long. So if the bear is 103 centimeters long, then my equation would predict that it would weigh 3.1667 times 103 minus 55.5033. So that would be 270.6668. So I'm going to say 270.7. I'm going to round that to one place. So in other words, what I'm saying is if the length of the bear is 103 centimeters, then I predict the bear would weigh, I'm going to just say I would predict y equals 270.6668, which I said I was going to round and then I didn't, kilograms. So 270.7 kilograms approximately. So 103 and 270.7 would be around right there on that red line. Now here's my point. We actually had a bear that was 103 centimeters long, and that bear actually weighed 274 kilograms, not 270.7 kilograms. So there is a difference between the value that we observed in the data and what our equation would have predicted. That difference between the predicted y value and the observed y value is called a residual, or an error. So there is error in our model. Our model did not accurately predict the weight of that 103 centimeter long bear. So the same would happen if I substituted the length of 102 into my model. If I did that, let's just do that. I would get 3.166 times 102 minus 55.5033. So if I had a 102 centimeter long bear, I would predict that that bear would weigh about 267.4 kilograms, which would be right here on that line, 267.4. But the 102 centimeter long bear actually weighed 264 kilograms, not 267 kilograms. So again, I have a residual or an error. My model has error. Now that would also happen if I used the blue line. And that would also happen to any other line that I draw through these data. There's always going to be a residual. So statisticians have agreed that the best line is the line that has the smallest amount of residuals. So if I were to find, like for all of this data, if I substituted 100 in my equation and found the predicted weight of the bear, and if I substituted 102 in my equation and find the predicted weight, and 103 and 101 and so on. So if I plug in all of the values for X into my equation and get the value of Y, each one of those is going to have some error. And so again, the equation that gives us the least amount of error will be the best line. Now there's a problem with that. First of all, what we're going to do in order to calculate the residual is we're going to find the difference between the predicted Y value and the actual Y value. So a residual is going to equal the observed Y value minus the predicted Y value. Now, notation-wise, to be able to tell the difference between an observed Y value and a predicted Y value, the observed Y value we're just going to call Y. I just realized I had that off the camera. So the observed Y value we're going to call Y. The predicted Y value we're going to call Y, and we're going to put a caret above it, an accent above it, and we call that Y hat. So we're going to do Y, the observed Y value, minus Y hat, the predicted Y value. So for example, for my 103 centimeter long bear, my observed Y value was 274, and my predicted Y value was 270.7, and so that was 3.3. So my residual right there was 3.3. That was my error. For the 102 centimeter bear, the observed weight was 264. So if I take 264 minus the predicted weight was 267.4, I never wrote that down. So minus 267.4, that is negative 3.4. So this residual right here was negative 3.4. So what's going to happen is when a point is above the line, we're going to get a positive residual. When a point is below the line, we're going to get a negative residual. So what's going to happen is if I did that for all of those points, about half of the residuals would be positive and about half of the residuals would be negative, so that if I just tried to like average them or something like that, if I added them up, they're going to result in 0. The trouble is that's going to happen no matter what line I do that for. So just looking for the least amount of residuals by themselves doesn't quite do the trick. So instead, we're going to not just look at the residuals by themselves, we're going to take all of the residuals and square them. When we square a negative residual, we get a positive result. When we square a positive residual, we get a positive result. And so if we add all of those up, that will be the sum of the squared residuals. And the line that has the smallest sum of squared residuals is the best line. Statisticians agree on that. So the best line is the line that has the smallest sum of squared residuals. So again, I would find the residuals for each point. I would square those and add those up. And the line that has the smallest sum of squared residuals is the best line that could possibly be drawn through those points. In this case, it would not be that red line. That would not be the best line. So what I'm getting at is the least squares regression criterion. The least squares regression line is the line that minimizes the sum of the squared errors or residuals. This line minimizes the sum of the squared vertical distances between the observed values of y and those predicted by the line, y hat. So there's that notation, y hat standing for predicted values. We represent this as minimize sigma residuals squared. So we are finding the sum of the residuals squared, the sum of the squared residuals. And the line that has the minimum sum of squared residuals, the smallest sum of squared residuals, is the best line. And again, that's called the least squares regression criterion.